Hello, let's get started. We have a whole, full house today. So it's our great pleasure to have Professor Jitendra Malik as a speaker in our William Mo Distinguished Lecture Series. Jitendra has worked on many different research topics in computer vision, graphics, machine learning, and robotics, and received many Best Paper Awards, including 3 times Long-Hedging Prize at CVPR and 3 times Helmholtz Prize at ICCV. And he also received many awards, including ACM 𝗶𝗶𝗹𝗶𝗀𝗃 Alan Newell Award and 𝗍𝗂𝗃 Award for Research Excellence. And he's also a member of US National Academy of Science and the National Academy of Engineering. So let me first ask David Sorowitz, the Dean of Engineering, to give welcome remarks.
So let me add my welcome to the one we just had. You know, it's a pleasure to see such a full room. I think we're in for a very exciting talk today. I'm excited to hear it. This talk is part of the William Mong Distinguished Lecture Series, which has been going on continuously since 1991 as a result of a bequest to the university from William Mong, who is the founder of the Shunhing Group. It's an engineering company, and this is one of his legacies in addition to that company. One of the pleasures I have as dean is I get to meet such interesting people and such important scientists and engineers, and I think this gives us an opportunity to see what's going on in the world, not just in our own field, but usually these talks are done in a way which helps those of us like me, who's not particularly expert in this area at all. Professor Malik, I mean, as you just heard, is quite a distinguished individual. I think one of his distinctions, besides what was just mentioned, is that he has supervised more than 80 PhD and postdoctoral fellows, and many of them are now professors at small universities around the world, including such mediocre places like MIT, Berkeley, University of Pennsylvania. So someday they'll aspire to be like Hong Kong. It's just going to be a question of time, and maybe they'll get here. Ah, okay. so I guess we're already in that select group. In addition to having many of his academic descendants at some of the larger computing companies, including Google and Meta. He's well known for his work in locomotion, navigation, manipulation, using robots. And one of the areas which I thought was particularly interesting that he mentioned in his abstract was that one of the difficulties in this field of trying to come up with intelligent robots is the question of how we can train. You know, we typically train almost everything we do now based on big data. And the world seems to be like such an obvious, easy place to get big data for robotics, but it sounds like it's much more difficult than I would have expected. And so there's a lot of applications of other methods, and I think we're looking forward to hearing about many of these things: reinforcement learning, sim-to-real transfer, multimodal perception, etc. So it's my great honor to introduce Professor Malik, and please join me in welcoming him, and we're all looking forward to an exciting talk. But before we do, sorry, it was a teaser. Before we do, though, what we try to do is present a small token of our appreciation in anticipation of a wonderful talk. So please join me.
Okay, I think all of us.
No, you.
Okay. Okay.
You in the middle. Sorry. We don't follow instructions.
I see. Thank you.
Okay.
Okay, thank
Now
you.
we'll let you go.
Okay. Thank you very much. Thank you very much for this very kind introduction. It is a pleasure to be here, and I look forward to talking about this theme, which is when will we have intelligent robots? So I like to start any talk on artificial intelligence by first talking about natural intelligence. Because if the term artificial intelligence is derived from intelligence, it's from the natural variety. And it's good to think about that in the context of evolution. So if we think about evolution, something like 540 million years ago, you had what's called the Cambrian explosion. So this is when you had a variety of multicellular animals emerge, and just this flowering of life, of different ways of life. And a key innovation at that time was that animals could move. And why was that an advantage? It was an advantage because that meant that you could get food in different places. But if you had to make use of that advantage, you need to know where to go, which means that you need to have some perception system. It could be vision, it could be echolocation in bats, but you need to know where to go. And there is this line from the psychologist: we see in order to move, and we move in order to see. And there is a lot that has been written on how this loop, where perception and action started to appear together, was crucial for the proliferation of life. Because, for example, some animal is a predator, some animal is a prey. So the prey is going to evolve camouflage, so the predator has to evolve a better vision system. The prey moves fast, then the predator has to move faster, and so on. So there is this evolutionary arms race. Now we can move closer to our present time and talk about when earliest humans split off from the primate line. And this is about like 5-7 million years ago. And a key step there was bipedalism. So we started to walk on two legs. So now the hands are free. And if the hands are free, they can build tools. And now that led to a growth of brain size. And there's a Greek philosopher, Anaxagoras, who said it's because of his being armed with hands that man is the most intelligent animal. So interestingly, the development of the hand precedes the development of the brain. And there are examples from the fossil record for that. And then somewhere in the last 100,000 years, million years, we don't know the exact date, we have the emergence of language, culture, abstract thinking. But if you think of the development of intelligence as 24 hours, language is in the last few minutes. Okay? And this is important to realize, because today the excitement about AI is all around large language models. And this is great. I mean, they are incredible and they have uses, and we are all impressed with what can be done. But in the story of intelligence, they're just the last 5 minutes. Most of the story of intelligence is really about the connection of perception to action. And that's the story that I want to talk about. So let's go further. What's happened here? So what are the central problems in robotics? Now, the engineering version of connecting perception to action is robotics. And what are the central problems of robotics? So people conventionally list these three: locomotion, which is moving about; navigation, which is moving about but knowing where to go; and manipulation. So I'll do a whirlwind tour, and it's a bias sample. I'm going to be talking about work from my research group largely, of where we are in each of these areas. So let's talk about locomotion. So I'll show you some results that we have in humanoid locomotion. So for those of you who have been to the US or seen pictures, these are places in San Francisco, intentionally chosen to be the beautiful spots. And this is a robot. This is the so-called digit robot walking around, and it can go on various trails and so on. And why I point this out is because a demonstration of an ability in the lab is one thing, but after that you want it to be real and robust. And this is what we can do, and I'll show you more examples later. Okay, let's move on. Okay, so this is hiking trails in the neighborhood of Berkeley. So these are in the hills, and this is a more serious test than just walking around on flat ground. And our robot has walked around for hours. Essentially, the limit is that the battery runs out and at some point. Okay, so these are results of locomotion. Okay, this is bipedal locomotion, which is harder than quadrupedal locomotion. I mean, navigation. What can we do in navigation? So I will show you this result, which is we call it GOAT, which has other meanings, but in our setting it is go to anything. So the experiment we did was the following. So navigation is the problem that I enter someone's house and I want to find a chair, or I'm in a restaurant and I need to find the restroom, right? These are navigation problems. You want to go to a certain object or location of interest. And again, this is a problem which people have worked on for decades in robotics. The question is, have we solved it? And the test for that is, does it work in the wild, in the real world? So the experiment that I put to my colleagues here, this is a big team, mainly this is work done at Meta, it was rent a random Airbnb. Okay, you don't have any knowledge of the Airbnb, you rent it, you open the door, you put the robot inside, you press a button or type a command which says go to the TV or go to the kitchen or go find a potted plant. And now you do this experiment in 10 different Airbnbs and you see how many times you succeed. So this is the test of success and robustness in the real world. And it turns out one can do this quite well. Okay, so that's the spot robot. And it's going to be given, this is the view, this is what it sees, the observation, and it's been given a goal, and a goal can be specified either as a picture or as some phrase in English. So here the picture is that of a kitchen sink, obviously. So what the robot is going to do is, it doesn't know where it is. So it's going to move, it's going to build a map of the environment, and it's going to declare success when it finds the kitchen sink. And it has been trained in simulation, so it knows what are plausible places to go to. So it should have a sense that you are more likely to find it in the kitchen than in a toilet, right? Okay, so let's see how it works. Let me play this video. Okay, so it's going around. That's what it's seeing, and it hasn't found the goal. It's building up some kind of a map. And okay, now we are about to get success. So now it's given a different goal, the lion, teddy bear, and the foosball table. So it's not found it yet. Okay, success, and so on. Now, as this is proceeding, it's actually building a map of the environment. So when it has it goes to a dead end, it will know not to repeat the dead end the second time round. Okay, you get the flavor of this. Okay, and then and this is a map being built of the environment, and then there are various locations. So it does not need to know a priori what the map of that apartment is. We just rented an Airbnb, we put the robot inside, and then these are the different locations, and then it can find it. And the performance here is on the order of like 90%. Okay, so we tested it on like 200 different object instances in these 10 different Airbnbs, and these are all the kinds of questions where find the plant in front of the window, the stuffed lion toy, the small wooden chair at the desk, etc., etc. So this is a measure of the success of the computer vision part, because you have to recognize objects, you have to build a map, and then you have to navigate avoiding obstacles. And this can all be done. And there are failure modes, and the failure modes have to do with, typically it is because the computer vision has failed. And that will get better, because the way our technology is for these deep learning based systems is we have more data, we train, so the model goes from 90% to 95% and so on. Okay, so that's the state of affairs on navigation. What about manipulation? So I'm going to start with a successful example. So this is from some group at Berkeley. And here what we have done is we are trying to do bimanual manipulation. Bimanual means two hands. And then each hand is a multi-fingered hand. And this is trained with some kind of behavior cloning. So you have a human do examples, and then the robot is going to replay those examples in some way. But it's being done autonomously. So let's look at this. Let's play this video. So there's a banana handover task. Okay, a tower block setting. So we picked these tasks because trying to do this with a parallel jaw gripper would be very hard. Like picking up this wine bottle with a parallel jaw gripper is a risky enterprise. And you see demos like this from many people now. There are many companies which are now claiming that they are going to solve physical intelligence or robotics or variations on this theme in the next couple of years. But for me, the test is how often does it work and how well does it generalize? Because I can, of course, cherry pick successes, right? And maybe it works in my kitchen, but no other kitchen. So in my view, the robustness of demos like the one that I'm showing you, but other people's, is, I think, as yet not proven. Okay, there isn't that test. Go to any kitchen in the, well, at least in California, and then your approach should work. Okay, so let's look at the report card. Okay, so this is to begin the talk. So the report card is what's the state of affairs in each of these areas. So I'm saying that locomotion, there's good progress. So I think the area of humanoids, there's a lot of work to be done. For quadruped locomotion, the problem is solved. For humanoids, it's not fully solved, but we know what to do. We have the machinery. We generally train in reinforcement learning in a simulator and then transfer to the real world. Navigation, I think of as nearly done. It's not so exciting as an academic research problem. If you are building a product, you will really want to get that last 99.999%. Manipulation, in my view, we are a long way away. Forget the capability of an adult or a skilled pianist or mechanist. We don't even have the capability of a 3-year-old child. We have a long way to go. Maybe it's like 20% of the way or 10% of the way. And then the question is, why? Why have we not succeeded in this, whereas we have these claims that GPT-4 can solve these amazing problems, do well at the law exam, etc., etc. And the answer is that there we had tons and tons of data on the web, like 1 trillion tokens on the web for language. Now, large language models are very inefficient in learning compared to human babies. And there's an estimate which is that they are like 10,000 times less efficient. And you can compute it fairly easily. There's data like a child of maybe 6 months old hears maybe 1 million words a month. At the age of 10, 100 times that, so that's 100 million. So 10,000 times that is 1 trillion. And that's the kind of data we use to train LLMs. So humans are much more efficient learners. They need much less data. And okay, so let's look. So this should motivate you, and it's motivated me, that let's look at how human babies learn can we take these ideas and convert them into engineering practice? And then we may have this recipe for how to manage with less data. Okay, why is there not data for robotics? We do not have trajectories of humans' thoughts and motor commands, the activations of your muscles. Do we have those trajectories? No, we don't. We are probably not going to give them up either. And even if we had those, there was a gap between the human and the robot. So there isn't a straightforward way of getting big data. Now, Alan Turing, who's considered sort of the father of computer science, he wrote this paper in 1950, which was about can machines think, and it's kind of considered like the foundation document of AI. But he has this line: instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? If this were then subjected to an appropriate course of education, one would obtain the adult brain. So this is a brilliant idea. So this is essentially resolving the nature-nurture debate, that you start with some basic capability, and then after that you subject it to education or training or development or whatever you want to call it. And can we do this? And in Turing's time, Turing wrote this as a mathematician or computer scientist. He was not a psychologist, and he had actually not studied how children learn. But in the last 70 years, and there was work even before that, our colleagues in psychology have done a lot. They've done a lot of scientific research from which we have insights into how children learn. And these are just various pictures, but I'll elaborate. For example, children's learning is very multimodal. They are interacting with toys, and they see things, and they hear things, and then they put things in your mouth. And so there are multiple signals that they're getting at the same time. They interact with the world. They're doing experiments with the world. So there's a book by Alison Gopnik called The Scientist in the Crib, referring to a toddler. Because when the kid is acting up and throwing stuff down from the feeding tray, you should think of it as, oh, she's actually doing a controlled experiment, okay, and learning something about the facts of physics, as well as learning something about social physics, like how the parents interact. So, here's a review paper from Smith and Gasser. These are child psychologists, and they came up with, they tried to boil down the wisdom of thousands of papers into some principles. And you can and should read the primary literature, but if you're an engineer who's busy and you have one paper to read this one, okay? And let me list some of the insights which I have sort of summarized. Multimodal. My example is the child has access to vision, touch, and proprioception. When you are touching an object, you have the touch signal from your receptors on your fingers. You're seeing the object, that's vision. Proprioception refers to the sensors in your muscles and joints, which essentially are measuring equivalent of joint angles. So you can, if you do the math of the kinematic chain, you can figure out the distance and position and so on. Incremental, we learn on top of previous knowledge, right? It's obvious we are in a university, professors teach, you build on what you think the student already knows. But this is true in children's education. This is not true in many of our systems where we try to learn tabula rasa, but that's not how it is. Skills are built on top of other skills. Physical embodiment matters, okay? Explore, that the child learns by exploration, not just by observation. This is interesting because this is a way to break the correlation versus causation gap. That's something which statisticians worry so much about. But the way to break that in statistical inference is what they call randomized control trials. You have an identical population, you split it into two groups, you do an experiment. Well, the child is doing those experiments. So the actual interaction part is important. Purely observational studies, you always have this correlation versus causation distinction. Social, we learn from others. We learn from observation of others. We learn from our parents, caregivers, and so on. We learn little practical things like how does a door open, that you turn a doorknob rather than push on it. And a handle turns, but if there's a certain other kind of handle you're going to pull or push. How do you learn that? Trial and error might take a long time. And if you think that this is not an issue, think of the following problem. Whenever you go to a strange hotel in a strange country, how long does it take you to figure out how to use the shower correctly and have the temperature right and the volume right? And it tells you that this is a challenge we always have. Okay, and then of course language. I mean, language provides abstractions, and we make use of that. So this is my high-level philosophy, and I think it's about operationalizing these very high-level principles. And I'm going to give you some concrete examples now to whet your appetite. So the first thing that I want to point out is something which I had to learn, because I came from a background in computer vision and pattern recognition, and then robotics is really closest to control theory. And what's a thing you have to learn? So in visual recognition, we knew about generalization. Generalization means that if you're recognizing dogs, you should be able to recognize any breed of dog from any camera angle, even if it's occluded by other objects, and if the lighting is different, and so on. So that's relevant here, because in robotics, if you're going to pick up an object, you should be able to pick up any object. If you're going to open a door handle, it should work for different doors, right? Now, keep this in mind, because when you'll see claims, outrageous claims for robots that are ready for the real world, you check them out on this. Are they actually proving that they can do generalization? The other thing to note is robustness to disturbances. I mean, this is the core idea of control theory, that you have you try to execute some plan, but whatever you try to execute, it's not going to operate perfectly. Your model will be wrong, there'll be noise, there'll be disturbances, and you make measurements and you correct. And that's a fundamental insight of control theory. So I like to put these together, that to build intelligent robots, we need to have robustness to disturbances, and yet we need to have adaptation to varying physical conditions. So I'm going to use one example, which is now it's like a few years old, but it's for quadruped locomotion, which, as I said, is now pretty much a solved problem. But it wasn't a solved problem when we first tackled this. This is a problem which, for example, Boston Dynamics had worked on for like decades. And but I'm going to use this to illustrate the new paradigm which learning brought to the table, where essentially what's happened now is that this is a setting where the learning-based approaches have now completely won the territory. Over the last 3-4 years, there was a tussle between these approaches such as MPC and reinforcement learning. But the latest stuff from Boston Dynamics, which was the temple of MPC, is that they have given up and they're using reinforcement learning now. So let's take an example. So in reinforcement learning, basically you train by trial and error. You try various actions, and you have a sequence of actions. And if that sequence of actions is profitable, meaning that you move all your legs, and if you land up moving forward and not falling, well, that's good, +1. You fall, -1, and you try to do more of the things which give you success rather than failure. So here you have this base policy and action A, which is, in this case, the joint angles of the robot. And you know the state X, which is also the joint angles, and the actions that you picked at time t-1. This is the only few slides which will have some equations on them, so hopefully you shouldn't be too bothered by this. Okay, and then it turns out that the right way to move depends on what physical conditions you are in. So there's this Z sub t, which you should think of as the environment. And the environment corresponds to, are you on solid ground? Are you on sand? Are you in a very soft place? Is it a sloping up, sloping down? All of that is captured in this unknown latent Z, which you don't know, right? Because this robot is, by the way, going to be blind. And so it turns out, so we have this technique which we call rapid motor adaptation. And the key idea was the way these external conditions become revealed to you by the response of the environment to your actions. So if I move and I take a step, and I apply the same force, and if I'm picking up my foot, if it's in sand, I apply that same force of whatever 10 newtons, and it won't come out, but if it's on hard ground, it will come out. So things like that reveal to you what the conditions are. So that previous history, which is over the previous 50 time steps of the actions you took and the way the state changed, that can be used to estimate these unknowns. So again, I'm skipping all the details, but I'll give you an example which is fun to watch. So here's this robot which is going to try to walk in this, and let's see what happens. What we are going to do is, okay, so is that it manages to do it, right? Okay, fine. Okay, and okay, let's see. I think I'm skipped. There's something which is missing in this video, so let's not worry about it. But the point of the video was that if you change the circumstances, so you put some oil on this mattress, then it starts to slip, but it recovers. And the way it recovers is by estimating this z, which is like some 8-dimensional vector which captures the hidden state. Okay, but let's look at what this means in the real world. So in the real world, we have this robot walking in many different conditions. So as I said, you want robustness and adaptivity, and we show that we can do that. So in these different settings, now note that these are not conditions that were there in the training environment. Okay, in the training environment, you varied the terrain, but we could not have possibly got all these conditions. Okay, now more modern versions of this are again walking bipeds, and here we use a transformer model, and then notice what it has to do here. Okay, so notice that its gait changes, it takes shorter steps, and if you have seen children who've just learned to walk, you'll see this kind of behavior. And what's going on here is, internally, you are trying to estimate what this external state is, and it is revealed to you by the consequences of your actions. And what these charts basically show is that in the neural network, which is the policy neural network, there is an estimation of the state going on. It's not explicitly being dictated by us. It needs to do this just in order to do the task successfully. And it emerges, quote, that's that magic word that people like to evoke, but it indeed does work. I'll give you another example, which is now, what do we need? So that was blind robots, by the way. Blind robots adapt to different conditions. Blind people can walk in different conditions. So what do you need vision for? What you need vision for is difficult conditions like steps, or if you have to cross a river on stepping stones. So, so we have some work on that, which I'll show the demo. The same spirit applies. You have to try to estimate some aspects of the environment. So we had some estimates of the environment were captured in this variable z, but there is this other variable gamma, which is capturing some geometry of the terrain, which is itself estimated from your previous observations. And let me show you this video. And this is like from 2022. At that time, this was a big deal, but if these ideas have now got widely adopted, and Unitree in particular, this is a robot made by Unitree. They have a demo video now which shows their robot jumping around in many conditions. But this transition from trying to use classical control, MPC, to reinforcement learning, particularly in these difficult conditions. This is one of the key results in that. But let me play this video because I like to show it off. So this robot has a camera in the front, and what you see in the top right is what it sees. So those are, so it's giving you some kind of a depth map. But notice how precarious and challenging this task is. If it gets even 1 foot placement wrong, it would fall. And we've done this experiment multiple times. It basically succeeds like 9 out of 10 trials on real stools, where it has no prior knowledge of it. And then, of course, climbing stairs. And basically, again, we have taken this in a wide variety of conditions, and I mean, this is robust. So the test is, can you take your robot, put it in different conditions, does it work? Right? It should work across the board. Without that, you're not ready for prime time. Okay, this demo I like to show. Okay, I wish there was the sound, but we will not try to achieve that. It's more effective when you hear the sound. But is it going to make it, is the question. Okay. So you got the point. Okay. Okay. So now I want to show. So this is what we can do. As I said, quadruped locomotion I regard as a solved problem. We first did the blind version, then we did the seeing version. With the seeing version, you can really deal with treacherous terrain. The biped version, the humanoid version, is much harder, because with 4 legs you are stable statically. With 2 legs, just being stable is a challenge. Now let me go back to these principles, and I'll try to show you vignettes of results where these principles gave us some help in coming up with new improved algorithms. So one is multimodality. So let me show you a benefit of that. So multimodality means that we have multiple senses, and I will show you results on this following task. Okay. So this is a task where you are rotating this object. There's some object, and again it could be any object, so that's the generalization part. And then this object is being rotated about different axes. So if you look at the coordinate frame in each of these photos, that shows what's the axis of rotation. So it could be the x-axis, y-axis, or the z-axis. So the third row is the z-axis, for example, and in the fourth row you show some random direction. And I mean, the point of this demo is that it can rotate any of a variety of objects and over a variety of different axes. And we've worked on this problem for like a couple of years. Again, I like to point out this problem as a challenging one, because you could not solve this problem by teleoperation. So today, teleoperation has become a very popular way of trying to train robots. So you have a human runs the robot through a task, you record the trajectory, and then after that you just play it back. And I'm saying that that will not work, because you have to adapt to whatever is the object and what the reaction is to that. Okay, and we did this problem first for the z-axis, and we were successful. And then we tried to do it for the x and y-axis, and it didn't work. And we tried a blind robot initially. And then it turned out that actually this, okay, so this is just showing the success. So again, I won't go into the details. Then we developed a fancier version of the policy. So the policy here is essentially what commands to use for your fingers, like how the fingers should move. So you have some joint angle, so you specify the change in joint angle. That's basically what's going on. But you have to be responding to the input you get. So if you have a blind robot, then the response it has is just the joint angles, the proprioception. And that's enough to do rotation about the z-axis. But suppose you want to do these more challenging tasks, rotation about the x or y-axis. Turns out the failure rate is very high, it just doesn't work. But if you put in a vision system, a little camera looking at the hand, and you put in each of these fingers, you put in a tactile sensor, so that when the object impinges on the finger, then you record the force that is being felt. Turns out that with that, it works. Again, the details of the system are not important. Basically, again, this idea of a z, which captures the unknown state of the object. This is itself being estimated from the past history, but you also have to do more sophisticated stuff like estimate the shape of the object and the contacts. Okay, this was the result that to me is the most important lesson from this, which is that we did these experiments on what's the value of different kinds of sensing. So there is the result with this. So this right bar corresponds to, this is work done in simulation, knowing the exact shape of the object. So this is like ground truth oracle knowledge. So then the performance is obviously the best. And then here you have a version where you have access to, oops, this mouse is not behaving. Okay, this version is when you only have access to proprioception. You have no sensing, no vision. I mean, proprioception is sensing. The joint angles are being sensed. But you don't have visual data, you don't have touch data. And the performance is poor. And as you add, so what the next two columns show is, what if you just add vision, or what if you just add touch? And the performance goes up, right? So this is just vision, this is just touch. And if you add both vision and touch, the performance is pretty close to having access to full ground truth knowledge. So this proves quite conclusively for this task that you'd need multiple signals. You need visual information, you need proprioceptive information, you need touch. The reason why I say, and this should be in a way is obvious, but the reason why this is interesting is because a lot of people in robotics have tried to manage without making use of tactile sensing. And there'll be even people who claim that this is unnecessary. And I think this is just wrong. When you have more sophisticated, challenging tasks, you want to have access to all the information. A simple task like opening a doorknob, it helps to have tactile information, because otherwise that will prevent your hand from slipping. When there's an object in your hand, one of the things we can do is the object doesn't fall and we apply only the right amount of force. When you're holding an egg, you apply relatively little force. If you're holding a heavy object, you apply more force. What happens is that you apply normal force, and then there is and that must be enough to resist sort of there's a downward weight due to gravity, and that normal force times mu, if you remember your physics, right? That's the thing that is there to prevent it from falling. And if you sense incipient slip from your tactile sensor, you just apply greater force. And we're doing this without thinking about it consciously all the time. So anyway, the moral from this is we are not going to solve robotics until we have multi-fingered hands and they have rich sensing. For example, the sensing we have in our fingers is tactile sensing. You want that. And you want vision. Okay. I'll keep going. So this area is, by the way, needs a lot of research. The number of people working on tactile sensing is like maybe 10 groups in the world. This is work from a group at Meta. And basically, this is like the most accurate tactile sensor there is in the world. You probably may not use it in this form in any product, but it gives you the scope of what is possible. So it's called Digit 360, and you have this, and it essentially is actually superhuman touch. So this is what's going on inside the sensor, and on the right I have a picture of a cross section of the human skin, and then there are these various sensors: Meissner corpuscle, Ruffini ending, Merkel disc receptor, and we have sensors which respond to low spatial frequency, high spatial frequency, low temporal frequency, high temporal frequency. How evolution managed to evolve this remarkable sensing system is, of course, amazing. But anyway, we tried to capture some of that inside the sensor. And with this kind of sensing, you can do stuff like if you pick up an object and you shake it, you'll know whether it's like a bottle half full with liquid. I mean, you'll get a signal for that with your tactile sensing. And I really do believe that we will not solve robotics without that kind of sophisticated sensing. Okay, and let me show you an example of another one of these capabilities, which is we tried to do this task, which is twisting the lid of a bottle. So the intended demo was to, okay, grandma is too weak to open her pill bottle, and now the robot comes and helps her. Well, it turned out we could not use these pill bottles because the hand is too thick. Okay, this is an Allegro hand, and the hand is like double the size of a human hand. So we had to, my student Toru had to print out, 3D print these objects which are kind of double the size of the bottles that we normally want to use. But that's how we could do the experiment. But let me show you some demos of how it works. Okay. And note the generalization, the same policy is working, and one hand, it's nothing is pre-programmed. It discovers this thing of one object kind of holding the hand and the other one twisting. And it's all learned in reinforcement learning. It may be that the way to make this more efficient is to first learn from imitation, observing humans, and then fine-tune it with practice on your own body. But again, you cannot do this task with teleop. It's just very challenging. It's very agile task because the sensing is changing all the time, and you have to make use of this. Okay. So I've given you a couple of these vignettes of manipulation tasks. I seem to be focused on rotation for some reason. Okay, rotating one object, rotating an object, or untwisting, which is also kind of a rotation. But, okay, I mean, how many, sounds like a new task, a new PhD thesis. Maybe it'll take 500 theses before we can solve robotics. So this would be a bit ridiculous, right? But this is actually analogous to what computer vision used to be like 25 years ago. You could get a PhD thesis for detecting faces. Okay, you could get another PhD thesis for detecting mushrooms, and so on. So is there a systematic way to think about what we want a robot to do in the home? And we didn't know what to do for manipulation, but I had worked previously on video analysis in a computer vision setting, and we had this data set we created called atomic visual actions. The set of actions, if you're watching a movie, is actually infinite. But if you operate at a time scale of 1 second, then it turns out that a fairly short list suffices. This is that list. And so if you're operating at a scale of time, a scale of 1 second, you have actions like walking, jumping, and so on that can be at 1 second scale. Or these are a single person, or you can have person-person interaction, or you can have person-object interactions. And we did a test where we took some movies and we asked people to annotate every second, and then there is the none of the above option, and then none of the above option is used 5% of the time. So it's not a complete list, but it covers like 95%. So in that spirit, we can ask the same question for manipulation, right? What do we do with our hands? And so the idea, by the way, just to repeat the point from the previous picture, there are, of course, very important events like birthday parties. But that set is infinite. Just like the set of sentences is infinite. But the set of words is not infinite. The set of words is like 100,000. Okay, the set of phonemes is like 100. But the set of sentences is infinite. So if you can get the atoms, and then you have compositionality, right? The number of molecules can be infinite. The number of atoms are only like 100 different elements. That's the idea we are trying to play with. It's an approximation, but let's see how far we go. And so we made up this list based on observations from videos. And these are examples. So notice that there's a lot of generalization. So these are all insert. So inserting a key, inserting Lego pieces, inserting a tool into its holder, etc., etc. So we can do that. I'm not saying that any of our robots today can do it, but this is to define the scope of the problem. So when people give you these very rosy picture of, oh, manipulation is about to be solved because we are just going to collect lots of trajectories by teleoperating robots, and then we will feed it into a VLM and it's going to all work. I want to know whether you can have the generality to solve all these variations. Cutting. By the way, there's no robot that I know which can effectively use a knife to cut a variety of vegetables. Zero. I'm not saying, something which works sometimes. No, nothing. Okay? So these are reasons to think that we've got a ways to go. Okay, these are actions without tools. So in fact, we made up some taxonomy. This simple task of, these drawers, pull and translate. So one of our colleagues, 𝗪𝗶𝗹𝗶𝗺, he had a student just go to many different homes and offices and just try to open these. And it turned out, and they had a policy which appeared to work really well. And then once they did this test, which is like the equivalent of the Airbnb test, and then basically they found it just works half the time. These problems are hard because there is a lot of variability in the world, and you need to be robust to that variability. When you collect trajectories in a particular lab setting, you're not going to get that variability. I mean, you might theoretically, I'm not saying never, but it is hard. So, so this is meant to be, and then these are examples with tools. So anyway, we try to make up this taxonomy of 20 different tasks. So we call these atomic manual actions. And we want to offer this as a challenge to the robotics community. So if you claim that you've got your robot which is about ready to be sold for $20,000 for your home, I want to first show you to do one demo, which is, okay, the cutting demo. You bring your robot to the lab, there'll be some knife, you won't know which kind of knife, we'll just provide some and you have to pick it up. And then I'll give you tomatoes and potatoes and zucchinis, and it has to work for everything. Only then and only then will I believe you in terms of your grant claims. And you do not get that when you just watch demos from the companies. You simply don't get that. Okay? Okay, by now I think I've elaborated. So, I want to conclude with what was I trying to say? I was trying to say, my big picture of my talk was locomotion, good shape. Navigation, nearly solved. Manipulation, this is what we have to be able to do. We have to start off with all these atomic skills. And I think our capabilities right now are actually quite limited. They are not as good as a 3-year-old child. And how will we get there? So now I want to have that positive message. How will we get there? So the answer is, I don't know for sure, but here is what I'm pursuing, and I will give you the ideas here. So I think that reinforcement learning has proved very successful for these agile skills like locomotion. I think that supervised learning with teleoperation, this is what is the current method du jour. Visual imitation, which is learning from observing others, so the child observing the parents. Now, I believe that a combination of these is necessary, but I feel that where we need to make maximum progress on is visual imitation. Because why is that great? It's great because essentially we have there the data already exists. There's 156 million hours of video on YouTube. So if you could find ways of learning skills, these atomic manual skills, in those 156 million hours, you have enough examples of every one of these skills. From that, you can get a sense of, for example, how door handles are operated. And if you get enough, and you have variety of different objects and so on. Once you get that, then we can try to train, then we'll have to do the transfer to a human. And here are some examples. So we can do learning to act from, this is a paper from like 2018, which showed that if I want to make my Atlas robot, this is in simulation, learn how to do a task, you can use the reference motion of a human doing this, and you can try to, at each stage, capture the pose of the human. Okay, and I'll show you now this paradigm. I'll try to finish in about 5 minutes. Like how can we use this big paradigm of, which has been very successful in language, which is next token prediction, okay? And so we are using transformers. So this is like the standard neural network used this way. And the idea is that you have observations and you have actions, and they form a sequence over time. And you can get these observations and sequences from, for example, watching these internet videos, right? In those internet videos, you have examples of the human body changing over time. And you feed these sequences and you try to solve the problem of next token prediction. And with that, you learn a model of how you do this. So here's an example. There's somebody walking, and now we are transferring that motion to this robot. And now we've got a robot trajectory, and in that space, we can do learning with this paradigm of next token prediction, which is the basic machinery which has been used successfully in language. And with this, we trained. So this was how I began my talk. And these examples were trained using this machinery of next token prediction. And this already was something. I mean, this was enabled us to do quite robust walking around all over San Francisco. And then, but this was not enough. What you find is that with this you learn, when you learn from imitation, then all you learn is imitation, right? Because all the examples in the training data, they determine what you can do. But you want to be able to do things which are beyond that, right? That's part of the human spirit. We don't just imitate, we do new creative things. So reinforcement learning is a good machinery for that because it's trial and error, so you can invent new things. And then if you have a reward function which gives you reward for doing interesting stuff, then you will do interesting stuff. So building from that model, we then train in simulation with reinforcement learning. And this enabled us to tackle like this challenge, which, by the way, there are lots of companies building humanoid robots. And I'll show you results which are better than any one of those companies. And this is like a group of a few PhD students competing with the big teams from I will not name all the big companies which are building and doing research on humanoids. So we live near San Francisco, and it's known for its steep hills. So Ilya, the student who led this project, he has put all these pictures of the slopes of the different hills, and let's see what we can do. Okay, so this is Jones Street, and it is a slope of, nobody can do this, no one else actually can do this. It's hard for you. If you try to walk on this, you're going to be tired. And then, of course, the question is, what is the steepest hill in San Francisco? It turns out it is Bedford, and this segment is a slope of 41%. So let's see if it can climb. Okay, now it's climbed all the way to the top. Do you think it can come down? Okay, it can actually, but here's the other obligatory test of robustness of the system. Okay, so I'm quite bullish on locomotion. I think we have tested it in a wide variety of conditions, and it works. Now, what ideas are relevant for solving the manipulation problem? And I'll do a few minutes on this. I think the secret is 3D. So we have tons of videos of humans doing tasks, right? Humans opening doors, humans chopping onions, humans doing there's some cooking process. And my belief is that the way to do this is to go from images to 3D, 3D of the hand and 3D of the object. And then we'll have trajectories of how the human did the task, and then we can get lots of examples, and then we will transfer from that capability from the human to the robot. But it's straightforward because when you have 3D, it's like you can put it into a simulator directly. And now I have to prove to you that we can do this 3Dification. And here are some results which show how we can find the hand and the object in 3D. But I think this next picture may be more convincing. So here's some video, and frame by frame, you're analyzing the hand and the object, and that side panel shows how the hand and the object looks like in 3D. So notice there's some jitter, so that means that it's not perfect because the estimates are noisy. Okay, but there are more examples like this. Okay, and this is what I'm betting on. I'm betting on that that the way to learn to transfer from human knowledge is by taking human videos, of which we have essentially an infinite amount, process them to find the hand and object in 3D, and now we have a trajectory of the human hand, and now we build a model of how humans interact with objects, then transfer that to a robot interacting with the object, make that trajectory robust, and when we can do this for all the common actions, then we will have kind of solved the problem. And we could take all those trajectories and put them into a VLM at that point, and it will work. But until that point, we are not there. These are examples more of showing that 3D reconstructions, right? So I think we are reasonably there. I don't regard it as fully solved, but it's close to solved. And at least that's what I'm building on. We can reconstruct the hands really well. And I'll say that this is where we should go. So this is more like a statement of philosophy. I regard these atomic skills as the hard problem. If we can solve that, we can do compositionality with techniques we know. Can we get robot dexterity at the level of a 5-year-old? Okay. And then the thesis is that we can compose skills to achieve tasks. And initially it will require planning, but then it will become a new skill. So think of, so my favorite example is learning to play tennis. The first time I go to a tennis court, I can actually play tennis with zero experience, because I'll drop a ball, I'll hit it with a racket, I'll get it across. Now the reason why it works is because each of those component skills, hitting a ball, knowing the physics of that a ball when dropped will fall down because of Newton's laws, etc., those I had from previous experiences, so I compose them together and I can play tennis. I'm not going to become Federer, right? For this I have to practice, and I have to practice in my own body. Just watching Federer will not make me Federer either. I have to practice, and I'll never get to be Federer. It's fine. But this is what I think is the operation of how skills are acquired. You do a little bit by observation and imitation, a little bit in your own body, and it becomes a skill. And we are constantly adding new skills to a repertoire, right? I mean, up to the age of 5, you had a lot of skills. That's why you could go to school. But then you learn to ride a bike. You learn to swim, right? Or at the age of 16, you learn to drive a car. It's built of components that you have. But this is, I think, the process of becoming physically intelligent. And I think I'll end here. Thank you.